This is Lesson 3 of the Subnetting.net video series on how to subnet. This lesson covers the Subnet Mask, Shorthand Notation, and how to calculate subnet ranges. Before we start, you should know that this is going to be the most difficult lesson of the subnetting series. If you've ever seen the movie The Karate Kid, you probably remember where he was told to wash and wax all of Mr. Miyagi's cars with the famous instructions, wax on, wax off. This lesson is going to feel a little bit like that. You are going to do some seemingly useless math exercises, but I promise you that everything you learn here is going to eventually come together in the end. We'll start with counting. If you were ever tasked with writing down all of the IPv4 addresses, starting with 0.0.0.0, it would look like this. We start in the fourth octet and increment by 1. So the next IP is 0.0.0.1, then .2, and so on to .254 and .255. So what comes next? Now we simply move to the next octet to the left and increment by 1. Then repeat. Once we get to the end of the third octet, we increment again. Now we move into the second octet. We continue on until we finish the second octet and eventually go through the first octet too. Once we have gotten to the highest IP of 255.255.255.255, we will have traversed over 4 billion possible IP addresses. Just to make sure you got it, here's a quick quiz. Order the following IP addresses from lowest to highest. If you need more time, pause the video. The correct answer is as shown. We'll come back to counting later in the lesson. In Lesson 1, we explained that networks can be separated into multiple subnetworks, which are called subnets for short. Let's start with an example. Suppose you're setting up the network for a restaurant chain. The network has a building where the main headquarters are located, and 14 restaurant locations, all of which are connected to the main headquarters. This complete setup is called a network. Each of the 15 locations has its own network too, but from the point of view of the overall network, we can say each location has its own subnetwork or subnet. Let's take a look at a hypothetical setup of one of the restaurant subnets. You can imagine that everything within the bounds of the ellipse is inside of this subnet. In order for this subnet to connect to the main restaurant network, we need to have a router. The router is shown on the boundary of the subnet to signify that it is the connection between this subnet and anything outside of the subnet. In its basic form, you can think of a router as connecting two or more networks together. In this case, it is connecting the restaurant subnet with the main headquarters network. On the inside of the restaurant subnet, we have a switch. Our devices might include some cash registers, a computer in the office, and a printer. Since all of these devices are on the same subnet, they are able to communicate with each other without using a router. In fact, we could even disconnect the router, and all of the devices could still communicate with each other if they were configured to be able to do so. But as soon as any of the devices needs to communicate with something outside of the subnet, then the router is required. Remember in Lesson 1, we discussed the fact that each device on a network has an IP address, and IP addresses in the same subnet can talk to each other without the use of a router. In Lesson 2, we learned about bits, and how the powers of 2 determine the number of different values we can represent based on the number of bits. Now we are going to combine the concepts of IP addresses and bits to learn about subnet masks. Inside of our restaurant subnet, there are 5 devices that need to have their own IP address. Can you name the 5 devices? They are the 2 cash registers, the workstation, the printer, and the router, not the switch. Remember that the router connects 2 or more networks, and in this case the router is in both the restaurant subnet and the main company network. So the router actually has 2 IP addresses, one for each of the networks it is connecting together. Note that the switch is still considered to be a device inside of the restaurant network, but it does not have to get an IP address. As you will learn in the switching videos, switches do not forward traffic based on IP. So now we know there are 5 devices that need an IP address in this subnet. In subnetting speak, these devices are also called hosts. So we would say we have 5 hosts in this subnet. The next step is to calculate the number of bits we need to represent 5 IP addresses. Before we do this calculation, we are going to add 2 to our 5 hosts. The reason we add 2 will be explained in the next lesson. For now, just remember that you should always add 2 to the number of hosts before calculating how many bits you need. So now we need to find the smallest power of 2 that is greater than or equal to 7, and that number is 2 to the 3rd power, or 8. This means the minimum number of bits we need for the hosts in this subnet is 3 bits. Just to make sure this is clear, suppose we had 7 hosts. 7 plus 2 is 9. The smallest power of 2 that is greater than or equal to 9 is 2 to the 4th power, which is 16. So if we had 7 hosts, we would have needed 4 bits. In subnetting, there are 2 different kinds of bits we need to calculate: host bits and subnet bits. We just determined that there are 3 host bits needed in our restaurant subnet. We'll show you how to determine the number of subnet bits in the next lesson. Here's a quick quiz. How many host bits are necessary to represent a subnet containing 50 hosts? If you need more time, just pause the video. The correct answer is 6 host bits are needed. First, remember that we must add 2 to the number of hosts, so our target number is 52. 2 to the 5th power is 32. 2 to the 6th power is 64. 64 is the smallest power of 2, which is greater than or equal to 52. Before we get into the subnet mask, let's do a quick refresher on binary. In Lesson 2, we showed you how to convert from decimal to binary, but we never practiced converting in the other direction, from binary to decimal. You'll need to be able to do this too, and here's how. Suppose you want to convert the binary number 1010 into decimal. First, we'll make it 8 bits long to line up with an 8-bit octet. Now we'll write out the 8 bits the same way we did in Lesson 2. To get the decimal value, simply add up the numbers below the ones. In this case, 8 and 2 add up to 10, so that is our decimal number. Here's another one. 10010010. Again, we write out the bits with their corresponding decimal values underneath. Then we add up the numbers below the ones. 128 plus 16 plus 2 equals 146 in decimal. Let's do one more. All ones. We write out the bits, and then we add them up. 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 equals 255. This is an important one to memorize because it comes up all the time. But it's easy to remember because it is the highest number you can represent with 8 bits. 2 to the 8th power is 256, but since we start at 0, the 256th number is 255. This is the highest number a single octet can have in an IP address. Earlier, we learned how to calculate the number of host bits for a subnet. Now let's learn how to create a subnet mask. But first, what exactly is a subnet mask? Simply, a subnet mask defines the range of IP addresses in a subnet. Note that just like IPv4 addresses, subnet masks also have exactly 32 bits. Let's write out the 32 bits for a subnet mask in binary. Now to make it easier for humans to read, we'll separate those 32 bits into 4 octets of 8 bits each, simply by adding periods. In decimal, that number equals 0.0.0.0. Now let's set all the bits to 1. In decimal, this number equals 255.255.255.255. Notice that both IP addresses and subnet masks contain 32 bits. But there is a very important difference between the two. IP addresses can have any combination of zeros and ones, and this is why there are 2 to the 32nd power, or over 4 billion different possible IPv4 addresses. But a subnet mask cannot have zeros and ones in any order. A subnet mask can only be made up of any number of ones followed by zeros. Note that the number of ones could be 0, so both of the numbers shown here are technically valid subnet masks. The first mask doesn't have any 1 bits, and it's followed by 32 0 bits. The second mask has 32 ones followed by no zeros. Since a subnet mask is constrained by the rule that it must have ones followed by zeros, there are a limited number of possible subnet masks. Can you figure out how many there are? The answer is 33. 1 for all zeros, plus 1 for each of the 32 bits that can be the last one in the mask. Here are some more examples of valid subnet masks and their decimal equivalents. Notice they are all 32 bits, and they all have some number of ones followed by zeros. Here is an example of an invalid subnet mask. When the number is listed in binary, it's easy to spot that this is an invalid subnet mask because it's obvious that a 1 appears to the right of a 0, and that's not allowed. Here's another quiz. Which of the following is a valid subnet mask? The correct answer is E. This is the only choice that has all ones on the left, followed by zeros. Now that you understand what a subnet mask is, let's create one based on the number of host bits. Remember, in our restaurant subnet we had 5 hosts, and we determined that we need 3 host bits to represent them. To create a subnet mask with 3 host bits, all we have to do is use 3 zeros. Converting this to decimal, our subnet mask can be written as 255.255.255.248. Let's do another one. Suppose we have 750 hosts. So how many bits do we need? 2 to the 8th power is 256, 2 to the 9th is 512, and 2 to the 10th is 1024, which is big enough. So the minimum number of bits to represent the number 752 is 10 bits. Now we create a subnet mask with 10 host bits. Converting this to decimal, our subnet mask is written as 255.255.252.0. Now you have seen 2 different ways to display a subnet mask: binary and decimal. Both of these are identical subnet masks written in 2 different ways. There is a third way to display a subnet mask called shorthand notation. It is written using a slash and the number of ones bits, and it looks like this. Notice the 22 is the number of ones in the subnet mask when written in binary. Again, all 3 of these numbers mean exactly the same thing. They are just written in different ways. Now that we know that shorthand notation is the number of 1 bits in the subnet mask, and the number of 0 bits in the subnet mask is the number of host bits, since we also know that a subnet mask always has 32 total bits, we can easily calculate one if we know the other. For example, if we have 7 host bits, then our subnet mask would be 32 minus 7, which is /25. Now that we know our subnet mask is /25, let's convert it to decimal notation. We start by writing it in binary, and that's easy to do because it's just 25 ones followed by 7 zeros. Now converting to decimal yields 255.255.255.128. Here's another quiz. What subnet mask should you use to accommodate 300 hosts? Write your answer in decimal notation. If you need more time, pause the video. The correct answer is 255.255.254.0. Here's how we arrived at the answer. 300 hosts requires a minimum of 9 bits. 2 to the 8th is 256, which isn't enough for 302. 2 to the 9th is 512, which is big enough, so we need 9 bits. 32 minus 9 is 23, so our subnet mask is /23. Now we write /23 in binary. And converting binary to decimal, we have 255.255.254.0. Now let's use a subnet mask together with an IP address. Suppose we have an IP address of 100.0.0.0 and a subnet mask of 255.255.255.248. We can write them together like this. Notice this time we wrote the subnet mask directly to the right of the IP address, separated by a space. This is a commonly used notation when specifying an IP address. Similarly, we can also write the IP address using shorthand notation. Notice when we use shorthand, we don't use the space. Once again, note that these two IP addresses along with the subnet mask are identical, just written in two different ways. Remember earlier in this lesson, we stated, a subnet mask defines the range of IP addresses in a subnet. Let's look at how this works. Here's an IP address with a subnet mask in shorthand notation. Remember that the /29 tells us that we have 32 minus 29, or 3 host bits. 2 to the third power is 8, so that means our subnet has 8 IP addresses in it. If instead of shorthand notation the subnet mask is written using decimal, like this, you have a couple of options. You could convert 248 into binary, then count the number of 0 bits, see there are 3, and then 2 to the third power equals 8, just like converting decimal into shorthand notation. Or you could use another trick. Since there are always 8 bits in an octet, and 2 to the 8th power is 256, you can also just subtract each octet's number from 256 and multiply them together. The first 3 octets are 256 minus 255 equals 1, and the last octet is 256 minus 248 equals 8. Multiply 1 times 1 times 1 times 8 equals 8 IP addresses. Notice that all of the octets with 255 in them will have no effect on the result, so you can simply skip them when you are doing the calculation. Now let's try this again for a different subnet mask. In this case, the /21 tells us that we have 32 minus 21, or 11 host bits. 2 to the 11th power is 2048, so that means our subnet has 2048 IP addresses in it. For decimal notation, we use our subtraction from 256 method. The first 2 octets are simply 256 minus 255 equals 1. The third octet is 256 minus 248 equals 8, and the fourth octet is 256 minus 0 equals 256. Multiplying them all together gives us 2048 IP addresses in this subnet. When talking about subnet ranges, sometimes we will refer to the subnet size. The subnet size is just a short way of saying the number of IP addresses in a subnet. Note this is not to be confused with the block size, which is something different and will be covered later in Lesson 5. When learning subnetting, it's a good idea to think about the subnet size because it helps you understand the underlying concepts. So let's look at our IP address again that has a subnet mask corresponding to a subnet size of 8 IP addresses. Now let's calculate the range of IPs. We'll start by listing out the 8 IP addresses in this subnet. The next subnet starts at the next address, which is .8. Now that we know the starting and ending IP addresses for this subnet, we can say that our range goes from 100.0.0.0 to 100.0.0.7. It's important to realize that when we calculate the IP address range for a subnet, we cannot simply start at any IP and count from there. For example, if our IP address ended with a 34 instead of a 0, you might be tempted to think the range of IPs would start at 100.0.0.34, like this. But that is not correct. Subnet ranges must always begin at an exact multiple of its own subnet size. So, for this example, anytime we have a subnet mask of /29, tells us the subnet size must be 8, and therefore the starting range of each subnet could only be one of the following. So that means the range of IPs for IP 100.0.0.34/29 would be 100.0.0.32 to 100.0.0.39. We know this because 32 is the highest multiple of 8 that is less than or equal to 34. Notice that to get the last IP in the range, instead of counting all of the IPs until we get to the last one, it's easier to go to the start of the next subnet and subtract one IP. So if our subnet starts at .32, the next one starts at .40, and therefore the last IP in our subnet is one less than 40, which is .39. Here's another quiz. What is the starting and ending IP address of the subnet that 100.0.0.150/26 is a part of? And what is the subnet size? If you need more time, pause the video. The correct answer is a starting IP of 100.0.0.128 and ending IP of 100.0.0.191, and the subnet size is 64. Here's how we arrived at the answer. A subnet mask of /26 tells us there are 32 minus 26, or 6 host bits. 2 to the 6th power equals 64 IPs in this subnet. This is also our subnet size. So our possible starting IP addresses for each subnet are 100.0.0.0. The next is the same, except the 4th octet ends in .64, then .128, and then .192. The highest starting IP that is still less than our IP address is the correct starting IP, and in this case it is the .128 address. The ending IP is simply the start of the next subnet minus 1, or .191. Here's another quick quiz. What are the starting and ending IP addresses of the subnet that 100.0.3.150 with a subnet mask of 255.255.254.0 is a part of? The answer is the starting IP is 100.0.2.0 and the ending IP is 100.0.3.255. Here's how we solved it. Let's start by calculating the subnet size. If we use the subtract each octet in the subnet mask from 256 method, we get 1 times 1 times 2 times 256, which equals 512. Or you can also calculate the subnet size by converting the decimal subnet mask to shorthand notation, which is /23. 32 minus 23 equals 11, and 2 to the 11th power is 512. So for a subnet size of 512, let's write down the possible starting IP addresses. The first one is 100.0.0.0, but what is 512 more than that? Well, remember at the beginning of this lesson we talked about counting IPs. Since we have to count beyond 256, we will need to use another octet. This means the start of the next subnet of 512 IP addresses is 100.0.2.0. The next subnet after that begins at 100.0.4.0. Our target IP of 100.0.3.150 is in the range of the subnet beginning with 100.0.2.0, so that is our starting IP address. Now we just get the IP address, which is one less than the start of the next subnet of 100.0.4.0, which is 100.0.3.255. In order to do subnetting quickly and accurately, it's important that you practice being able to convert between the decimal subnet mask and shorthand notation. On Subnetting.net, go to the Choose a Question Type page and work on the first two question types. This is the end of Lesson 3, which covered subnet masks, shorthand notation, and how to calculate subnet ranges.